In this section, we will discuss foundational aspects of multi-threading that are necessary to better understand what we do while we are programming in multi-threading environment. We will start by discussing processes. Then we will discuss threads, what threads are, why they are important in modern software development, and how they are implemented by the major operating systems. When you run a program on your computer or start a new service on your server, the operating system creates a process that contains the program code and data. It's up to the operating system to manage the process until the program terminates. Several processes can execute simultaneously, and the operating system is responsible for allocating resources to each process. This allows for multiple programs to run on the same computer at the same time without interfering with each other. Each process works independently, running with its memory space and having its unique execution context. This means that each process has its own CPU stack and can run separately from the others. The operating system takes charge of managing processes, ensuring that each of them gets the computational resources it needs to progress with processing in an efficient manner. Finally, the operating system also implements the required inter-process communication mechanisms. This involves exchanging messages between processes based on some form of message exchange, such as pipes and sockets. The process control block is a crucial data structure used by the operating system to manage processes. The PCB typically includes information such as the process ID, priority level, scheduling state, and CPU register values, as well as the memory management information. It also keeps track of the resources used by the process, such as I/O devices, open file, and network connection. The PCB is created when the associated process is created. The operating system uses the PCB to manage the process lifecycle. This involves scheduling the process for execution on the CPU, switching between different processes, and saving and restoring process execution context when switching between them. While specific contents of the PCB may vary depending on the operating system and its implementation, the PCB remains a critical component of every modern operating system. By storing comprehensive information about each process and process resource usage, the PCB enables efficient and effective management of system resources. This is essential for ensuring stability, reliability, and security of a computer system. In modern software, it is very common to have multi-threaded application. An application is typically implemented as a separate process with several threads of control. Also, the operating system kernel takes advantage of multi-threading. For instance, when Linux systems are booted up, several kernel threads are generated that implement specific tasks, including device management, memory management, and interrupt handling. Threads are entities that operate independently within the same process, and threads share memory and execution time. This is very important. Let me add that each thread has its own stack where function calls and local variables are stored during the runtime. Threads can communicate with each other through models and primitives based on shared memory. In a multi-threading parlance, we say that threads synchronize their execution via shared memory models. We will discuss these aspects of multi-threading in great detail in this class. Similarly to process control block, in multi-threading we have thread control block, TCB. TCB is used to store information about thread state, execution context, and scheduling information. This information include thread ID, priority, scheduling status, CPU register, stack pointer, and synchronization object. The specifics of TCB may vary depending on the operating system implementation, but these information are quite common. The TCB is created when a thread is created and is critical to effectively manage thread multi-threading operating systems, including scheduling for its execution on the CPU, switching between threads, and saving and restoring thread executions context during context switches. This figure is a recap of the main concept we have discussed so far. In our model, now we have application. Application may be composed of one or more processes, and each process may be composed of a number of threads of execution. In particular, for each process, we have the process control block, a user address space, which is shared among the different threads, and the thread of execution that implement the application. For every thread we have the TCB, the thread control block, along with the user stack and system stack. Multi-threading comes with a number of advantages. First of all, economy. Creating and terminating a process, allocating memory and resources, implementing the context switch among processes that are executing on a CPU is a very time-consuming activity that requires a significant amount of resources. On the opposite, creating threads is highly efficient, and therefore threads are often dubbed as lightweight processes. A second advantage is the efficiency in resource sharing. Threads by default share system resources, share the same memory, share the I/O, and as a consequence it's very simple to implement highly efficient thread coordination mechanism and to share resources among different threads. Threads also enable a better use of multiprocessor architecture. Today's system provide a number of CPU or CPU core, and the operating system can allocate different threads to these available resources, to these available CPUs or CPU core in a transparent way. So it's not up to the application to take care of this optimization. It is the operating system that enables parallel execution of different threads on all available computational resources. Finally, responsiveness. Some application thread can progress in execution even if other threads are blocked. For example, it is quite common to have a thread implementing some I/O application, and this thread may have to wait for the I/O to complete, for example, to complete file reading. At the same time, we don't have to wait for this I/O, but we can use the time, for example, to run a different thread, implementing some other task, possibly some processing in memory with available data. As a result, the application implemented via multi-threading appear really responsive to the user. And this is a very important advantage for interactive application. So far, we have briefly discussed about a really important aspect in multi-threading programming. Basically, the concept that threads share the same address space and that coordination among different threads is based on the use of shared memory, of this shared memory. This approach to thread coordination is really simple and highly efficient. However, the coordination through shared memory can be tricky. For example, Conflicts may potentially arise when two threads attempt to write the same variable. With the increasing complex of modern CPU, it's really challenging to implement efficient application level or even kernel level primitives to address these issues. As a result, modern CPU provide privileged atomic instructions that are necessary for the implementation of multi-threading primitives. Atomic instructions cannot be interrupted. They are executed without interleaving and cannot be split by other instructions. When the CPU detects an atomic instruction, all other instructions in various stages of execution are suspended, and maybe they are reissued later until the instruction completes the execution. When the CPU recognizes an atomic instruction, this atomic instruction will be the only instruction enabled to run on the CPU, and all other instructions are stopped. Also, interrupts are disabled. When this atomic instruction completes, all other instructions can have to be reissued and refetched. If two atomic instructions are issued at the very same time, even on different CPU or CPU core, they will be executed sequentially. This privileged instruction, in general, can execute only in the supervisor or kernel mode. Example of privileged instruction are test and set or compare and swap instruction. We will discuss them with more detail in the following. To facilitate the creation and management of threads, a thread library provides programmers with an API. There are two main approaches to developing a thread library. The first method involves constructing a library entirely in user space without operating system level support. The library code and data structure are therefore entirely located within the user space, and the resulting threads are often referred as user threads. Any operation executed in the library triggers a local function call within the user space rather than a system call at kernel level. The second method is developing a kernel level thread library. This library requires operating system support, and in this case, the library code and data structure exists in kernel space. Whenever a function within the library API is invoked, it generally results in a system call to the kernel. This approach employs the so-called kernel threads. All major operating systems, including macOS, Linux, and Windows, provide support for kernel-level threads. Let's make some consideration about user threads and kernel threads. Well, user threads provide support at the user level without any intervention from the kernel. As a result, thread library implemented in user space tend to be more efficient. However, if a thread is blocked, all the threads executing within the same process are also stopped. This is an important shortcoming, and it's no surprise that major operating systems opted for kernel level support of multi-threading. However, it's clear that providing support for multi-threading at kernel level may require to identify a relationship of, if you prefer, a mapping between the thread implementing the application, the user thread, and their actual counterpart at kernel level that are managed by the operating system. According to hardware and operating system characteristics, The kernel may run threads on different processes and core and may adopt different mapping approaches. In the following, we will discuss many-to-one model, one-to-one model, and the many-to-many model. In the many-to-one model, various user-level threads are mapped to a single kernel thread. The thread management functionality is implemented by the thread library in the user space. The model is very simple, but has several limitations. Whenever a running thread executes a blocking system call, the entire process is blocked, leading to system inefficiency. In addition, the model cannot take advantage of computational resources provided by multi-core system, as multiple threads cannot be executed in parallel. Due to its extreme simplicity and despite its limitation, the many-to-one model was adopted by the early releases of the Java Virtual Machine. The one-to-one model associates every user thread with a dedicated kernel thread, offering support for actual parallel thread execution. This addresses the issues and limitations of the many-to-one model we discussed before. In fact, the one-to-one model enables other threads to run when one thread makes a blocking system call. It also permits the execution of multiple threads in parallel on multi-core processor. The only downside of this model is that generating a user thread requires the creation of the corresponding kernel thread, and a considerable number of kernel threads may decrease the overall system performance. Despite this technical limitation, it's worth noticing that this model is quite popular, and the main operating systems currently implement the one-to-one multi-threading models. In particular, both Windows and Linux operating system rely on the one-to-one multi-threading model. The many-to-many model is a thread model that allows many user threads to be multiplexed to a small number of kernel threads. The number of kernel threads available may vary depending on specific operating systems. These models offer really efficient parallel execution on multiprocessor or multi-core devices, and allows the kernel to schedule another thread for execution when a thread made a blocking system call. Despite its efficiency, this model is quite difficult to implement and has become less important in the last few years. Let's discuss interleaved, parallel, and concurrent processes. Here we use the term process in general, and as process may identify either processes or threads. The execution of a process is said to be interleaved when all processes are in progress, but not all of them are running at the same time. In this case, it's up to the operating system to assign each process, or each thread, if you prefer, some CPU time, and to let them progress in their execution. The execution of processes is parallel when all processes are running at the same time. An example is depicted in the figure, where process 1, 2, and 3 are executing at the same time. Process interleaving and parallelism are not alternative models. As you can see in the figure, we have process 1 and 2 that are executing in parallel, and their execution is interleaved with the execution of process 3 and 4. It's up to the operating system to take care of process scheduling and allocation on available CPU or CPU cores. We can finally discuss concurrency. The execution of processes is concurrent if it is either interleaved or parallel. a concurrent program with multiple threads can run in parallel if computational resources are available, as computational resources would mean CPUs or CPU core. Otherwise, the operating system can assign each thread with some CPU time to let them progress in their execution. Notice that the distinction between concurrency and parallelism exists. A concurrent system supports more than one task by allowing all tasks to make progress, whereas a parallel system can perform more than one task simultaneously. It is therefore possible to have concurrency without parallelism. Let's have a look on processes and threads on a real system. Now you can see my console, the console of my Mac, and by using the top command you can have a look to the processes and threads that are running on my system. Here you can see the result of the execution of top on my machine. As you can see from this figure, we have 328 processes running on my machine. 2 processes are actually running, whereas 326 are sleeping. In addition, 1,388 threads are also running in my system. The top command can also be used in Linux to have the full visibility of processes and threads that are running into the system. In particular, if we consider the option H, we can have the visibility of currently running threads. Here is the result of the execution of the top command on my Linux box. In particular, here we have 462 threads, one is running and 424 are sleeping. This concludes the first section of our class. During this section, we discuss foundational concepts that are really useful for understanding multi-thread programming. We introduce the concept of process, then we discuss threads, what threads are, why they are important in programming, and how they are implemented by the major operating systems. Now let's start to consider Python multi-thread programming. Let's get started.